So in order to find vorticity, we need to take cross product of del with u. So here's del, it's a vector. I don't know if you're really supposed to put a vector sign over or not, but it is a vector. And of course u is a vector, so we're going to take that cross product to find the vorticity. Del is d by dx, d by dy, d by dz, a three-element vector of the three derivatives, and u is u, v, and w, which are of course the x, y, and z velocities in Cartesian coordinates. In order to find the vorticity vector, it is a vector, also has three elements, we take the cross product of those two things. The way you do that is I put them in two rows. I have d by dx, d by dy, d by dz, del in the top row, u, v, and w in the second row. And in order to find the x component of the vorticity, I cover the column corresponding to x, and I take the determinant of the remaining four. So I have dw dy minus dv dz. That's my determinant, plus minus, and I get dw dy minus dv dz. So that is the x component of vorticity. For the y component of vorticity, I cover the y component, and I take the negative of the determinant. So it's dw dx minus du dz, but with a negative sign in front. So negative dw dx minus du dz. I put that negative sign through, I get du dz minus dw dx. That is my y component of my vorticity. My z component of vorticity, I cover the z column, and I get dv dx minus du dy. So dv dx minus du dy. If you look at your notes or look back at the last lecture, you'll see that this is the one that we calculated when we were looking at that square and how it rotates. So we arrived at this as a definition of rotation in the flow based on the fact that rotation is caused by dv dx and du dy terms in the two-dimensional flow case. So we'll look at the two-dimensional flow case in a little more detail here so you can see what vorticity looks like in 2D based on this mathematical formula. So first I'll take a look at the x component of vorticity. So I'm going to take a look at the x component of vorticity, which we know because we just showed it was dw dy minus dv dz. So that's the x component. But what does it mean to be a 2D flow? So in two-dimensional flow, w equals 0 because there is no z velocity, and d by dz is equal to 0 because nothing is changing in the z direction. So if we apply that to this, well, w is 0 and d by dz is 0. So those both go to 0. So that whole term goes to 0. If we look at the y component of the vorticity, we see the y component was du dz minus dw dx. Well, d by dz is 0 again because it's two dimensions and nothing happening in the z direction. And dw dx, well, w is 0 again, so we get 0 for that. So we also get 0 for the y component of vorticity. The z component of vorticity in two dimensions, or in any dimensions, is dv dx minus du dy. But those terms don't have w's or d by dz's in them. So this is the only non-zero term in 2D flow. So in two-dimensional flow, in 2D, you don't really need to worry about all the different terms of the vorticity. The first two terms are always 0, and the last term is the only non-zero term. So that's the vorticity vector in two dimensions, because you really can only have rotation in the direction of the page if it's a 2D flow. So that's always going to be your z dimension of vorticity, because you go to the curl is going to give you the right-hand rule. So the z component is the one that tells you whether it's rotating in the plane of the page. And you can't have rotation like this or rotation or the other rotation because you can't, that would go into the z dimension. So you're only going to have rotation in the plane of the 2D plane, and that's only going to give you a z component of vorticity.